Hi guys, assalamu alaikum. This is Arif. In this video, we are going to see how we can design shift left logic using structural design first in Verilog, system Verilog, and then in VHDL. So this is a system Verilog program first, and here I have defined a module, and its name is shift left logic, and it is an 8-bit program, and it has one output as two inputs A and B, and here we have defined those outputs and inputs as 8 bits, and after that we have to understand its design. So shift left logic is here we are going to see the input B, and we are going to use its first 3 bits because our A is 7 bits, so that means that 3 bits of B are only necessary to vary and shift the values of A. And if A is going to be like 32 bits, then B's 5 bits we have to use. But in this case, first 3 bits of B we are going to use input, and we are going to see the value of the first 3 bits of input B, and we are going to shift the bits of A accordingly. So this is the way this program is going to work. So after that, we can design shift left logic using Verilog code like this. These lines which I have commented out, and here we can see that, for example, if B is going to be 000, so we are going to concatenate nothing, and we are going to say that assign A this input as it is to S output, and then we are going to say if B is 1, that means we have to shift by 1, and we are going to say using the slicing and concatenation, we are going to say from the right side insert a 0 and shift the other bits towards the higher bits is 6 to 0. We are going to shift on 7 to 1 bits, and this is the way we can shift. And then we can say if B's value is 2, and then we can say okay, insert two zeros from the right side and shift the other bits towards the left, and same with insert three zeros, four zeros, and this is actually the logic, the way we can design this VHDL code. But this is behavioral design, and in order to convert this into a structural design, what we can do is we can use this logic instead. And in order to understand this logic, you can search on internet as well. Here we are going to use only 3 lines instead of these 8 lines. And this logic, the way it works is we can understand it from a flow chart or a flow diagram. And that flow diagram, the way it is going to work is we are going to first of all do one shift using this S1, and we are going to say okay, if B0, which is this value, first bit of B, least significant bit of B, so if this is going to be 0, so either we are going to insert A to the output, or we are going to shift A by 0. So we are going to insert 0 from this side using slicing and concatenation, and we are going to say if B0's value is going to 1, so shift by 1 using a 0 from the right side, assign like this, the way we are doing here in these 8 lines. Then we are going to use this same S1, and we are going to say these two things are covered. First two, 000 and 001 are now covered. Now we are going to say okay, now check B1, the second bit, and if it is going to be 1, what we are going to do, we are going to say okay, shift S1 by 2 bits, and here we are going to do, here we are using the same two zeros, right? And we are going to say else if this B1 is 0 like two previous cases, then just insert same S1 to S2, and otherwise we are saying that if it is going to be 1, then shift by two zeros. So this is the way we are going to cover these four scenarios, first four scenarios, and after that For next four scenarios, we are going to say, okay, now use S2. And what we are doing is using the S2, we are saying check now the third bit, this one. This is becoming 1 here, 1, 1, 1. And we are going to say, okay, if this bit is 0, then take this S2 and give it to S. But if this bit is 1 like this, for the next four cases, then shift by 4. We are actually inserting from the right side 0 at this point. And the next three combinations we are going to use using these previous combinations. That's why we are using S2 here instead of A. So this S2 is going to cover all the previous four combinations, but it is going to give us the next four combinations according to this third bit, this B2 as well. So this is actually the logic, very simple kind of a logic. So this is the complete program. I have compiled it already. Now I am going to show you its result using simulation. For the test bench, let me show you first the test bench as well. So the way the test bench is written is, since S is output, so we are going to define it as a wire, and after that we are defining A and B as reg because these are the inputs, and after that we are calling here that same module from our design shift left logic 8, and we are going to insert these signals like this, and we are going to map those values of inputs and outputs like this, and then we are going to have this initial block, and here what we are doing is we are first assigning at 0 time 0 values to both A and B, and after 10 nanoseconds we are going to start this for loop, and we are going to increase the values of A by 4, and we are going to increase the values of B by 1. And after that what we are doing here is we are going to give another combination so that we can check more combinations as well as our input. So this is the complete test bench. I am going to simulate this. So first we have to check how shift left logic is working, and then we are going to modify this code into a structural design code. So this is the way the output is going to be. If the A is 4 and shift by 1, it is going to become 8, and if A is 8, shifting by 2, B's value is here, is going to make it like this, and same way these all are going to work. So now using this three code lines, what we can see is that these are actually muxes. Okay, if select input is like 0, select this. If select input is 1, select this. So what we can do is we can define another module, and this is going to be used as a mux. So we have defined outside this module another module which is mux 2 to 1, and it is also a 8-bit mux, and this has two inputs and then a select input and then an output. And here we are defining the inputs and outputs like this. So select is just 1 bit, the others are 8 bits, and then we are going to say assign to output input 1 if select is going to be 1, and otherwise the input 0 should be assigned to output. And this is actually the way we design the mux. And now using this mux, what we are going to do is we are going to say okay, so now we are going to implement the above line using a mux. We are going to say okay, this is the input 0. So if B0 is going to be 0, this is the input which we are going to assign to our output S1. Okay, and then we are going to say, okay, if B0 is 1, then assign this slicing and concatenation, which is going to actually shift the A signal by 1 and insert a 0 from the right side, and we are going to then assign this to this using structural modeling. And after that we can skip this line as well and include this line. Same mux 2 to 1 8-bit we are going to use here as well, and we are going to say, okay, now if B1 is going to be 0, assign this S1 which we are getting from here to S2, and otherwise assign this one, the same thing which we have written here up in the above line. And now we can exclude this third line and include this line. This is actually called the structural modeling, the same pattern. Now we can actually save this file. Simulate this test bench. Go to this wave window. Select these signals, the inputs and outputs, drag those to the wave window, run, and we are going to see the same output. So this is actually the structural modeling using Verilog of a shift left logic design. And now we are going to actually flip over to our VHDL project, and we are going to see how we can do the same stuff using VHDL language. So this is now a VHDL project, and this is its design file. And here first I am going to explain you this shift left logic. Here we have again defined an output 7 bit, the 8 bits, two inputs A and B, 8 bits, and our entity's name is shift left logic. And after that, what we are doing here is we are actually going inside this begin block, and we have to define the same logic of our shift left logic, and the way we have defined that is here. So according to the B's values, like first 3 bits of the B, whatever value they are going to give us, we are going to use those to shift our A signal or A port, and then we are going to assign that to the S. So this is output, and we are shifting A here towards the left side and adding the zeros, and according to these B values, B2 down to 0. So using this logic, actually now we can design our code like this in the behavioral model, and we can say, okay, check first bit of B0, and if it is going to be 1, then shift towards the left by 1 and add a 0 towards the right side, else give A as it is to S1, and then again we are going to say, okay, now check this second bit. So if B1 is going to be 1, shift S1 towards the left side by 2 and add 2 zeros from the right side. And then we are going to say, okay, now check the third bit B2. If it is going to be 1, then shift towards the left side by 4 and add 4 zeros. And these 3 combinations are going to give us these 8 combinations. Let me show you its output as well. It is going to be same using behavioral model. So this is our output. This is same as previous case, so I am not going to explain this. And this is actually the test bench as well written. So test bench, the entity name is test bench, just like in Verilog. And after that, we are going to start the architecture of the test bench, and we are going to call this component, which the main entity of our design code shift left logic, as a component in this architecture. And after that, we are going to use these signals to map those values using this port map. Here we are going to call that same entity of our design shift left logic. And after that, in this process block, we are going to say, okay, A is going to be 0 0 at first, B is also going to be 0 0. After 10 nanoseconds, we are going to say on this for loop, vary these values, and then we are going to use the A and B values like this as well, so that we can check most of the combinations possible. So now actually what we are going to do here, like Verilog, we are going to see that these all code lines are actually logics of our mux, the way we design mux. So we can say, okay, if the select line, which is going to be in this case, this B1 is going to be 1, then input should be this one, otherwise input, this one should go towards the output, the way the mux is. So using the same code line, we have defined here an entity mux 2 to 1, which is 8 bit. We are going to say input 0 7 bit, and input 1 7, the 8 bit, sorry, select line 1 bit, output O is also going to be 8 bit. And then we are going to say architecture of the muxes, and inside this begin block we are going to say, okay, if select input is 1, then input 1 should go to the output, otherwise input 0, same logic. And after defining this entity code, what we are going to do is we are going to use the same entity, we are going to skip these code lines, and we are going to say, okay, using this mux 2 to 1 8 bit, we are going to say port map this thing. So what we are going to do is we are going to at the input 0, we are going to say A should be inserted. And at input 1, using this slicing and concatenation, whatever we used here to shift those bits, same this part we are going to place here. And then we are going to say this is the select, and B0 is going to be our select signal, and this is going to be output. And then after that, we are going to skip this code line and do the same logic using a mux, and same mux we are going to say now, okay, this is input 0 s1, and then input 1 should be this one, the same like in the above line, this one, this part. And then we are going to say instead of select, use this b1 here, and then this is going to be our output. And then we are going to the same pattern, skip this line and use the same mux here. So this is the way actually we are going to do the structural design of a shift left logic using VHDL. Let's save this program, compile, go to library window, simulate, drag these to this wave window, run, expand the signal, and we are going to see the same shifted output of S and according to our two inputs A and B. So this is the way actually we can convert our behavioral design into a structural design. I hope you guys have enjoyed this video. Have fun.